So it's 10:30. I think so let's get started. So welcome everyone to the SNAPP seminar series. And today we are very happy to have Professor Budhiraja joining us. Professor Budhiraja is a professor of statistics and operations research at the University of North Carolina at Chapel Hill. His research interests include stochastic networks, stochastic control, stochastic differential games, theory of large deviations, nonlinear filtering, and stochastic dynamical systems. He has written many excellent papers on these variety of topics. And so today he's going to talk about near equilibrium fluctuations for certain supermarket models. So Amarjit, the floor is yours.
Thank you very much. And thanks a lot to the organizers for giving me the opportunity to speak in this very nice seminar series. I think this is an excellent idea, and I hope we are able to sustain it even beyond this pandemic. So today, I want to talk about some scaling limit results for a class of queuing systems that have been a focus of much recent research, motivated by applications from load balancing for large parallel server networks. And the work that I'm presenting here is joint with Shankar Bhamidi and Miheer Dewaskar, and this is part of Miheer's dissertation. And Miheer is in the audience, and he's going to be monitoring the chat boxes and has promised to answer all the hard questions. So I'm glad to have Miheer here. Okay, so let me continue. So here is the let me just. Okay, so here is the basic setting of the queuing network that I'm interested in. So we have a processing system with n parallel queues, with each queue having its own dedicated server, and server processes jobs at rate 1, and the arrivals to the system occur at rate n lambda n. So the arrival rates scale with the system size. And we are in the usual Markovian setting, so all inter-arrival times and service times are exponential, and the usual mutual independence assumptions. So this bullet kind of describes the main characterizing feature of this model. Each arriving job, it randomly selects dn queues, and it joins the shortest among them. And of course, this is a quite now well-known model. So in the special case where dn is n, this is the very well-studied join the shortest queue system. When on the other extreme, when dn is 1, because of this Markovian assumption, this simply reduces to n independent MM1 queues, and everything is known about that system. And the case dn equals d is usually referred to as the power of d scheme, and that's the setting that we'll be interested in. So these JSQ dn schemes, as I said earlier, are motivated by these load balancing problems, and they have been studied extensively. And this is an excellent survey article by these authors, which talks about the various applications and also the state of the art in this topic, at least until a couple of years ago. Two important papers in this field are the ones listed here, which observe that in the subcritical regime there is a significant improvement in performance when one increases d from 1 to 2. Specifically, if one looks at the tails of the asymptotic steady-state distributions, then of course when d is 1, we know they decay exponentially. But when d is 2, these tails decay much faster, super exponentially. So this improvement is sometimes referred to as power of 2 or power of d. Although there is a huge improvement in going from d equals 1 to d equals 2, it has been observed and argued in this survey and in this paper that no fixed d kind of can match the optimal waiting time properties of d equals n, the join the shortest queue system. So then a natural thing to consider is to consider the number of choices that increase with system size. And that's what we will be interested in, namely situations where dn is a function of n, and it goes to infinity as n goes to infinity. And our goal is to study the asymptotic properties of the system as the system approaches criticality. So the arrival rate lambda n is approaching 1 and dn approaches infinity. So in order to set the stage for the kind of results we're going to show, let me now introduce some notation. So GNIT here will denote the fraction of queues in the nth system at time instant t with at least I customers. So for example, GN0t will always be 1, and GNIT is greater than or equal to GNI plus 1t. So it's a non-increasing sequence. And the object that we'll consider is this vector valued process GNT, which is just this vector GN1, GN2, GN3, so on. And this vector, you can view it as the cumulative distribution function of the empirical distribution of the queue lengths, more precisely 1 minus the cumulative distribution function. So it's easy to see that this GN as a stochastic process has sample paths in this space where this L1 down is just a subset of L1, which consists of sequences which are summable, non-negative, and non-increasing. And it has a topology that it inherits from L1. Okay, so this is going to be our object of interest, and this is sometimes also referred to as the state occupancy process. And so the law of large number behavior of GN was studied in this very nice paper of Mukherjee et al. And I'm going to refer to this paper quite a bit, so I'll abbreviate it like this with apologies to the authors. And so this is one of the results that shown in their paper, that if you consider a vector R in this space L1 down, and suppose the initial occupancy state converges to R in this space, and suppose the arrival rates lambda n, they converge to some lambda, and this lambda could be less than 1, greater than 1, equal to 1, whatever. And dn approaches infinity in an arbitrary manner. It can be extremely slow. Then this paper showed that GN is a tight sequence in this function space. And if you look at any subsequential weak limit, which are denoted here by G hat, that satisfies a set of equations, the so-called fluid limit equations. And the fluid limit equations are a bit hard to, notationally a bit hard to write, so I'm not doing that here. And one thing is that, this paper doesn't quite show that there is a unique solution to that fluid system equation. So it only shows tightness and write down equations for the limit point. But there is an equivalent way to describe this these limit points using a one-dimensional square-chord map, from which it is quite easy to argue that this system of equations, in fact, has a unique solution. And then this result can be strengthened not just to tightness, but actually to convergence. And that was, an observation made in this paper with Shankar and Miheer. So this is how this representation looks like. So this representation is going to be given in terms of a square-chord map. So for a level alpha in R, so alpha is a real number, gamma alpha will denote the square-chord map at the associated with the level alpha, which keeps trajectories below the level alpha. More precisely, for any function h in this path space, if H0 is less than or equal to alpha, we denote the constrained version of H by the following formula. It's very familiar to us. Just remember what this represents is a trajectory which always stays below the level alpha. And this gamma hat alpha is the corresponding pushing term at the level alpha. Then it can be shown that there is a unique solution to this infinite system of equations. So we have this vector valued functions g and v, and the ith coordinate function gi solves this integral equation involving the square root map at the level 1, and vi is the corresponding pushing term at the level 1, and that is given by the following equation. And I'll observe that the equation for the ith g involves the I plus 1th g, and it also involves the pushing term associated with the I minus 1th. So these are all coupled, and it's an infinite system of equations. And by pretty elementary methods, one can argue that this system of equations has a unique solution. And in fact, this is the same system of equations as appears in this paper of Mukherjee et al. And then it follows from there that this occupancy process converges to G, which is described through this system of equations. So our interest here is actually in studying fluctuations and more precisely equilibrium fluctuations. And those type of results actually go earlier than the paper of Mukherjee et al. And there's this nice paper of Eschenfeld and Gamarnik, which considered the case where join the shortest cube, so dn is equal to n here. And they consider the critical regime, so lambda n approaches 1 in this fashion, so sometimes also referred to as the half-invit regime. And they consider the occupancy process centered around the vector E1. So E1 is the vector 1, 0, 0, 0, so on, and which is scaled by square root of n. And this is what the result says. Suppose the initial centered and scaled occupancy state converges to some limit y. And let's assume for simplicity that this y has all but finitely many coordinates 0. So all coordinates after r are 0. It's not needed, but it simplifies the statement. Then one can show that this process yn, now a process in this path space, converges to a stochastic process y. And this y is a finite dimensional process. In fact, all coordinates beyond r are 0. And for the remaining r coordinates, one can write down a system of equations. The important feature of this system of equations is that it is there is essentially a one-dimensional Brownian motion which is driving the system of equations. So, for example, in the special case when r is 2, this is just reduces to a two-dimensional system of equations, and this is how it looks like. So the first coordinate is given by given as a solution of a reflected stochastic differential equation, and I'll just observe that the first coordinate equation involves the second coordinate, and the second coordinate equation involves the local time associated with the first coordinate. You can equivalently write this in terms of a two-dimensional square root map on the half space, but perhaps this is clearer way to say this. And I'll also maybe remark here that in this paper of Eschenfeld and Gamarnik, the convergence was shown component-wise or in R infinity instead of L2. But to strengthen it to L2 is an elementary step. Okay. So then there was the nice paper that I mentioned earlier, where the case dn less than n was studied. Specifically, this paper considered the regime where dn grows faster than square root of n log n. And their main result is that in this regime, one gets exactly the same limit theorem as in the case dn equals n. And the proof is based on some very nice coupling ideas. Talk much about that. But there are two things I want to emphasize. One thing is that this paper observes that that this is in some sense the right quantity to look at, in that if dn over square root of n log n converges to 0, then the process yn, this centered and scaled occupancy process, cannot even be tight. So there is no hope for a limit theorem of the form in this paper when this quantity approaches 0. And the other thing I'll observe is that the paper doesn't make any comment on the boundary case, what happens in the boundary case when dn is of basically the same order as square root of n log n. So yeah, so our goal in this work is to understand the asymptotic behavior in a more general setting where dn can approach infinity in an arbitrary manner. So specifically, we're interested in situations where dn is not as fast as in grows as fast as in this paper. Okay, so in order to kind of say what kind of results we are seeking, or what kind of results to expect, I want to take a step back and talk about one phrase that I used previously, that these are equilibrium fluctuations, and say what that means. So the observation is that if you look at this centered occupancy process considered in these previous papers, the centering is around the point E1. And this point E1, easy to check that it's a fixed point of the fluid limit equations associated with the state occupancy process in this critical regime when lambda n approaches 1. And so these two previous papers are really studying fluctuations about an equilibrium point. And so that's why the term equilibrium fluctuations. Turns out that this is not the only equilibrium point of this ODE. In fact, this ODE has uncountably infinite equilibrium points. And a typical equilibrium point can be written in this manner. First, say k coordinates are 1, and the next coordinate is a number between 0 and 1. And all of these stationary points, they arise in a very natural fashion. And I like to say how they show up in the queuing system. So the state process for the queuing system, can be described through an evolution equation of this type. So let me just remind you that this is an infinite dimensional system, and so this is an infinite vector valued process. And this is a martingale, which is also infinite dimensional. One can check that this martingale converges to 0 as n goes to infinity. And here A, N, and B are some maps, and they're very explicit. One can write them out, but notationally it gets crowded, so I'm not saying what these maps are. And they're maps from L1 down to L1. Now, since this martingale converges to 0 as n becomes large, for large n, this stochastic process, roughly speaking, is close to the solution of this ordinary differential equation. Again, an infinite dimensional ODE. Turns out that this ODE actually has a unique fixed point, which is obtained by solving setting the right hand side to be equal to 0, and there's a unique place where the right hand side is equal to 0. And this unique stationary point of this ODE is what I denote as mu n. Again, I'm not writing what mu n is, but it's not hard to write. It is very explicit in these parameters lambda n and dn. Since mu n is a fixed point of this ODE, and this ODE is formally close to this state process, we refer to this mu n as the near fixed point of the state process Gn. And the point is that if one allows dn to go to infinity in a suitable manner and lambda n approaching criticality in a suitable manner, this mu n can converge to any of these fixed points, uncountably many fixed points that I had shown earlier. So from that, it follows that if you consider a suitable initial condition, the state occupancy process can converge to any of these fixed point solutions as n goes to infinity by suitably choosing dn and lambda n as a function of n. So that's what I meant, that any of these fixed points arises in a very natural fashion from this Gn. So right, so and so that's what we are now trying to do. We're trying to study fluctuations of the occupancy process about this near fixed point. So this allows us to explore many different kinds of fixed points of this ODE. And so the scaling is the same square root of n scaling. So this is our object of interest, Zn, but the centering this time is mu n rather than the fixed point E1. And the observation is that in the regime considered in this paper of Mukherjee et al., where dn grows faster than root n log n, this half-Linwick regime, turns out that it doesn't matter whether you center using mu n or you center using E1, because this quantity converges to some positive number alpha. And so, the asymptotic behavior of Zn can be just read off from the asymptotic behavior of Yn. But in general, this quantity may diverge, or more quantity of this type where you use a different fixed point may diverge. And so the behavior of Zn and Yn could be quite different. And that's where, that's what allows us to make some progress in this case, in different choices of Dn. Okay. So I just want to give you some flavor of the type of results we obtain. So, suppose that this initial centered occupancy process and scaled occupancy process converges to some limit, little z in L2. And once again, for simplicity, let's assume that it has all but finitely many coordinates 0. And in our limit theorems, as I said, we'll allow dn to go to infinity in an arbitrary fashion. And depending on dn, lambda n will approach 1 in a suitable manner. There are different ways to present these results. One can describe dn in terms of lambda n's or lambda n's in terms of dn, but this is perhaps a more convenient way to do this. We consider the following three regimes. The first regime is where dn grows slower than square root of n. And then the second regime where dn is more or less like square root of n, and the third one where dn is faster than square root of n. And the general result that we have is that in each of these regimes, this process Zn converges to some limit object z in this path space. And this z is relatively simple in that it has all but finitely many coordinates 0. And the finitely many coordinates, once more, you can write a system of equations for them. And this system of equations is driven by a one-dimensional Brownian motion. But the type of the system one gets, that depends from one case to another. It's quite different in the three different cases. And in fact, one can get a very rich asymptotic behavior depending on how dn and lambda n approach their limit. And I'm just kind of listing some possible things that you could observe in the limit. In the limit, you could simply have a one-dimensional Brownian motion. That's it. That's what the limit system is. Or you could have a one-dimensional Ornstein-Uhlenberg process. You could have a linear diffusion which has only the kth and k plus 1th coordinate 0, non-zero, and every other coordinate is 0. And k could be arbitrary. It could be as large as you wish. Or you could have a linear diffusion, with first r coordinates non-zero and remaining coordinates 0. And again, r could be arbitrary. Or you could have a diffusion which actually has an exponential drift coefficient. On the right-hand side, we have a function which depends on the state process through an exponential function. Or we could have a state process like in Eschenfeld and Gamarnik, where you get reflected diffusions, which are coupled with r other state processes. Okay, and I'll show you examples of this. But what I want to maybe comment on is that we are kind of used to half-Linwick type regimes, and so I want to say that these results do cover lambda n's which approach 1 in this manner. So for example, when a is equal to half, this is the usual half-Linwick regime. If a is larger than half, then this is the super half-Linwick, and if a is less than 1, maybe sub half-Linwick. And all regimes are, for example, possible in this setting where dn grows slower than root n. And where Dn grows faster than root n, once again, some half-in-width regimes are included. All of super half-in-width regimes are included, and the half-in-width regime is included as well. But when Dn over root n approaches C, some positive C, then you don't quite get to the half-in-width regime, but you can get arbitrarily close to it. So essentially, these are the range of A's that are allowed in this regime. Okay. So I just want to show you the form of the limits in the three cases. So let me first start with case A, where the growth is very slow, slower than root n. And in that case, this is how the system looks like. You don't have to pay close attention to it. The point about the system is that it has its first k coordinates 0, and all coordinates after r are 0. So really, there are only equations from k up to r. And this system of equations are linear. So these are linear SDEs. Actually, there is only one-dimensional Brownian motion which appears in the kth coordinate, and the remaining coordinates don't have any Brownian motion. I should maybe comment on this approximately equal to 0. I mean, the thing is, if the initial condition limit, it is exactly equal to 0 in the first k coordinates, then this can be approximately be replaced to exactly equal to 0 as a process. But if the initial value is non-zero, then what happens is that almost instantaneously this process becomes 0. And to say this in a rigorous fashion, one has to take some care, and you can find the details in the paper. So I'm not going to spend time on that. So, but the basic picture is like this. So there are two parameters here. There is the parameter k, which tells you which coordinates are non-zero, and this parameter alpha, which sort of captures, which shows up as this drift. And these parameters, they depend again in a manner in which lambda n approaches 1 in relation to dn. Okay. So maybe a couple of other comments on this in this regime. If one considers lambda n approaching 1 in this manner, so for again, when a is half, this is the half-in-width, and then a is larger than half, super half-in-width, and so on. In that case, if one takes dn growing in this manner, then the theorem is satisfied. So for example, when a is half, this could be n to the power half log n, and something, and k needs to be bigger than 1, right? In that case, so this of course gives examples where dn increases in a polynomial way, but in fact it also covers cases where dn can grow really slowly. For example, dn could be log of n, and but then of course lambda n must approach 1 also very slowly, and this is how lambda n must approach 1. And then again, the limit theorem that I presented holds in that cases. So the other thing that I'll observe is that in both of these cases, you only see non-zero fluctuations in the kth and the k plus 1th coordinate. And you can choose k to be arbitrary by choosing, dn suitably or lambda n suitably. And this quantity k, you can view it as the measure of wait time experienced by the job. So the larger the k, the worse is the wait time. And as one might expect, the higher values of k, they correspond to higher traffic intensity, as you can see from this relationship here, and lower rates of increases of dn, and which you can see from this relationship here. And so there is a very intuitive connection between what k appears in terms of lambda n and dn. The final comment that I'll make is that in these examples that I gave here, mu n actually converges to fk. So you can think of these results giving sort of fluctuations about this fixed point, approximately, roughly. Yeah. Okay. So the next is this case, where dn over root n converges to c, where c is some fixed scalar. In that case, the system of equations looks like that. Again, you don't have to pay close attention to it. All you need to observe is that it has finitely many coordinates non-zero. After that, it is 0. And it's a one-dimensional Brownian motion that is driving the system. It only shows up in the first equation. And this time, you don't have a linear diffusion, but you have these coefficients which depend exponentially on Z1. So there is this one parameter alpha that appears here, and this alpha depends on how dn and lambda n approach infinity. Couple of comments here. This exponential drift may make you nervous, but there's no problem with explosion in finite time because of this negative sign here. So it works out. So this equation has a unique pathwise solution. Oh yeah, so the other point that I want to make is that if you look at what this drift looks like, as C becomes larger and larger, you see that there is this drift becomes more and more negative whenever Z1 is larger than alpha because of this term here. So when C becomes larger and larger, you get stronger and stronger push towards the negative side when Z1 becomes larger than alpha. And in fact, when C approaches infinity, this term, formally approaches a reflection at the level alpha. And that's actually what we see in the regime when dn over root n goes to infinity. You actually see a reflection at the level alpha. On the other hand, when C approaches 0, this term just dissolves, and you just get a linear diffusion that we saw in case A. So this regime very nicely interpolates between the linear diffusion case and the reflected diffusion case through this exponential drift, which gets stronger and stronger as C becomes larger and larger. I'd like to make one comment here. In the business of queuing that we are in, we are used to seeing reflection terms arising from idle times. In this example, in this model, the reflections are arising through a somewhat different phenomena. It's not, there are no idle times here. We're not looking at queue lengths. We're looking at occupancy processes. And this result shows you, the exact fashion in which these reflections appear. For C equals 0, you don't see any reflection, and then slowly you see stronger and stronger drift, and as C becomes infinity, you start seeing reflections. Okay. And I just list a few examples, which are covered in this case, but maybe I'll skip this. Okay. The final regime is where dn over root n approaches infinity. So that's dn is faster than root n. And then you actually start seeing these reflected diffusions. So remember, this is the reflection at the level alpha, which keeps the process below the level alpha. So once again, you get a finite dimensional system. All coordinates after R are 0. And in the first coordinate is given through a reflected SDE, and the remaining coordinates, are these linear equations. And let me also observe that the local time of Z1 appears in the evolution of Z2. Okay, so this is how the limit looks like. And the observation is that if one makes dn to be a little bit faster, so right now we just assume dn is faster than root n, but if dn is faster than root n log n, then we are in the regime of Mukherjee et al. If, for example, lambda n approaches 1, in this manner, so the half-infinite regime, they covered the case where alpha is strictly positive, but you can also allow alpha to be 0, but then you have to say a little bit more how it approaches 0, how fast it approaches 0. And so I'm not saying that precisely here. In that case, turns out that you can actually also study the asymptotics of yn, where the centering is now not mu n, but it is E1. And yes, you recover the result of Mukherjee et al., which gives a limit theorem of this type. And note that now the reflection is not at alpha, but it is at 0. And the reason is because you are centering using E1 rather than mu n, and that takes care of that. Okay. So the other observation is that this result actually also covers the borderline case, which was not discussed in Mukherjee et al. Namely, the case dn is root n log n, more or less. And lambda n is of this form. So note that this is the half-infinite regime, because root n 1 minus lambda n converges to A. And in this case, once more, you can say that, with the usual centering, with E1, for example, rather than mu n, yn converges, and the limit is the same that I showed earlier, with one important difference, that the reflection now is not at 0, but at -a. So you have there is a different behavior that appears in this boundary case, that now the reflection is not at 0, but at -a for this process. So yeah, and the other observation I have is that depending on how lambda n approaches 1, the reflection can occur at any barrier. And in fact, alpha equals infinity is possible as well, in which case you don't see reflection. And these are few examples of this regime. So once again, if A equals half is the half-in-width regime, and so on. These are the various, this is a super half-in-width regime, this is the half-in-width and the sub-half-in-width. You see, in each of these cases, if Bn grows like this, Bn depends on A, and the higher the traffic, the higher the value of Bn. So that's the behavior that you see. In these regimes, this reflected diffusions appear. So in particular, reflected diffusion appear not just in the half-in-width regime, they also show up in these other regimes. Okay, so I just have a couple of open problems. I was suggested that I should make some comment on some open problems. So the one observation is that recall that there are many fixed points of this fluid limit, and a typical fixed point looks like that. And the limit theorems that I showed you, in case B and C, the fast regimes, they correspond to the setting where this near fixed point mu n converges to F1, which is same as E1. Whereas case A, it allows mu n to approach to any fixed point of this type, Fk, for any k, k however large. But none of these cases actually cover the case where mu n converges to a fixed point of the form Fk gamma, where gamma is strictly between 0 and 1. And you can easily give conditions under which, where mu n converges, this near fixed point converges to one of these crazy fixed points. For example, if dn grows slower than n to the power 1 over k plus 1, and lambda n is of this form, 1 minus lambda n is of this form, then one can actually show that mu n converges to this crazy fixed point, fixed point where gamma is between 0 and 1. But we don't have a fluctuation result in this regime at this point. So that's one open problem. The other open problem is that all the theorems that I showed today were finite time results. And what about the long time behavior, convergence of stationary distributions and stuff like that? Okay, so those are a couple of things that might be interesting to think about. This result kind of gives a deceptive picture, that all regimes are covered. But the thing is that in the three regimes that I talked about, you make some assumptions on lambda n, and you say if lambda n is like this, then you get a limit theorem of this type. But that's not an exhaustive kind of a description. So there are other limit behaviors possible here which are yet not covered in the results that we have presented. And I think there is more to be done here. Okay, so these are some references that I pointed to, which were mentioned in this talk. And yeah, thank you.
Thanks, Amarjit, for a very clear and interesting talk. I still have quite some time for questions.
Maybe I'll start with one. So Amarjit, you mentioned about the long-term behavior as being open.
Yeah.
So do you have any results on at least the stationary distribution of the limiting process, at least in some of the cases?
A very good question. So the thing is that if you look at the limit process, it's as you observe, it's driven by a one-dimensional Brownian motion, and so it's not. It's a degenerate diffusion. For example, even arguing the uniqueness of a stationary distribution there, it requires work, and you kind of have to show that there's some kind of irreducibility, right? That type of behavior you have to show, and it requires work. And I'm not saying that it's there are fundamental challenges, but it hasn't been sorted out yet. Yeah.
I see. Thanks.
Amarjit, Venkat, I have a question related to your very interesting talk. It's mostly just more like a conceptual thought. So when you have DN, which is significant in the regimes that you're talking about, or even the ones that was considered in the Mukherjee et al. Paper, you might think that there would be some benefit from modifying the scheme in the following way. I mean, you're going to be picking DN queues anyway. And if you sort of lucked out and found one of the queues to be very small, it might be helpful to retain that in your memory.
Yeah.
And then to just pick another DN-1 queues the next time around.
Yeah.
And the guess would be that this would kill the kinds of fluctuations that you're observing in the regime that you're studying. So I was just wondering if you had any thoughts about that.
This is very good question. I mean, that's a model which is actually of significant interest, and people have been investigating that. What happens to the fluctuations there? I can see the intuition that that this type of fluctuation behavior perhaps would not appear. But I don't have a very well thought out answer that what would you expect and what type of fluctuations one should focus on. I haven't thought about that problem, but it's very interesting. Yeah.
Okay, thank you.
Yeah.
So I have a rather basic question. So I was looking at the slide 6 of the presentation, and then there's the Skorohod map, which is reflected at yeah, there you go, the GI and then the VI, and then they're reflected at 1, where we're having alpha equals 1.
Yeah.
Could you maybe just elaborate a little bit more on the intuition as to how that takes place?
So as far as the definition of this GI is concerned, right, means it is basically so gamma 1 is simply defined like this, right? So it is so that's what where it shows up. So yeah, so in order to see how it arises, you kind of have to go to the state equations and kind of see how the evolution is changes when an arrival occurs, when all the jobs, for example, all the queues have at least one job. And so what these equations are trying to do is saying, well, okay, you formally add that arrival to G1, but since it is not allowed, you have to compensate for that. So this reflection term is sort of compensating for that. And but at the same time, that arrival must go to G2, and that's why you see in the equation of G2, you see a local time term. And so this is just a record-keeping device that of how these Skorohod map appears. I may not have explained it too clearly, but that's the idea that you kind of first formally put it in this equation for G1, but then say, okay, this is now bigger than 1, so you have to kind of bring it down.
Okay.
Lesser
I see,
than 1. Yeah.
I see. Okay. Yeah. That's, yeah. Thank you.
So can I ask a question?
Oh, hi, Rami.
Hi, thanks for the talk. So
Thanks.
the drift is sometimes linear and sometimes exponential.
Right.
Is there a simple intuitive explanation for that? When this happens?
So, I guess you could even ask that sometimes there's a reflection and there's not a reflection. So the way
That's right.
so really there's a whole gradation of behavior, right? There is a linear drift, there's a stronger and stronger exponential drift, and there is then a super strong drift which translates into a reflection. And this, you see this transition as the DNs are becoming larger and larger, right? Means I mean, in the first regime, you see no exponential drift where DN is slow, and then when DN is like root n, you see an exponential drift, and when DN is faster than root n, you start seeing reflection. So that's the rough behavior. Now, where does the exponential drift comes from? It essentially comes from the behavior of this near fixed point. What happened here? Sorry, mu n. So I didn't actually tell you what this mu n is. I'm sorry, I kind of lost track of mu n.
I think it's on page 11.
I can't find it now.
I think it's
Okay. Yeah.
on
Here.
page.
Yeah. So mu n. So really, it is the behavior of mu n which is producing different types of drifts. And in the regime that we considered, if you look at the asymptotics of mu n's, so remember mu n kind of, they depend on this behavior of lambda n and dn. So that terms, converges to an exponential factor, and that's producing the exponential drift. Miheer, maybe you can make some more comments here. It's sort of kind of, that's where I recall the exponential drift is coming from. Do you have anything to add here?
Yeah, so I think so you have this ODE equation, right? Gn,
right.
The derivative of Gn is given by this right side here.
Yeah.
So this an term, which also this an function which depends on n.
Yeah.
I think that term when we center it with the fixed point mu n, the limiting behavior of that term behaves linearly when dn in the first case, and it behaves non-linearly in the second and third cases. So that's where.
So all the game is really trying to understand how the shape of mu n looks like in different regimes, and that's where these various different behaviors show up.
Thanks.
Yeah.
I have one more question.
Yeah.
So in case one, mu n was basically all ones up to kth component and then zeros afterwards. And then you're having fluctuation on the boundary, basically on the kth component and the k plus 1th component. But in case B, for example, mu n is just 1 followed by all zeros, but then fluctuations are not just in the first and second component, but they're going all the way up to rth component. Why is that? Is there
That's deceptive? That's deceptive. So that's the case even in the kth case. So so let me show you the limit. So the thing is, suppose you take the initial conditions to be 0. Take the initial conditions to be exactly equal to 0. Then you just see k and k plus 1th.
Okay. It's the same thing in case B as well. If you take initial condition to be 0, it's just those two components. Okay.
Yeah.
Thanks.
Yeah.
So it seems that there's no more questions. Let's thank the speaker again. Thanks, Amarjit, for a very clear talk. Now feel free to stick around if you just want to chat a little bit. I think we still have a bit of time if Amarjit don't mind sticking around.
I'm here, no problem.
Yeah.
Thank you. Yeah, thanks very much again.
Thank you.